Good afternoon. We begin lecture 19. We'll do a quick summary of the points covered in lecture number 18. We have started discussing the example from Say and Vishwanath. We will continue and complete the discussion. As I mentioned, the goal of this example, it's a very simple example but gives us a lot of insight into the behavior of wireless systems. So that is the important thing that I would like to focus upon in today's lecture. After this, having gotten a basic understanding of how relay fading works and what are some of the other aspects of wireless channels from the example, we then move our focus towards what modulation methods can we use and which are the ones that are most attractive for a wireless channel. So we move into a broader area of modulation and the corresponding methods of detection. We will focus initially on the modulation and the performance of the modulation. So again, it is a fairly vast topic. As you know, there are different types of modulation schemes, which ones are most suitable for our wireless channel, and maybe in today's lecture we start to give you a feel for what are some of the considerations that we need to take into account once we want to make a decision regarding the modulation. During the doubt clearing session, a few students indicated that they would like to have a full problem solved on Erlang B. Again, if that is a broader interest in the class, I will do that in the next lecture. Just give me an indication after the class is over. Otherwise, we will do a worked example during the revision session on Thursday. So this is again more to understand some of the questions that arose in the context of assignment number 3 and also in preparation for the first quiz. So let's move into a quick summary of the points that we were mentioned. So as a student of wireless communications or having studied wireless communications, if somebody were to tell you, I'm making the assumptions that the channel is a rarely fading channel, what are some of the assumptions that they are making? Can you just quickly run through the things that you remember? What is it that makes a channel a rarely fading channel? Very quickly. Non-line of sight. Very good. Okay. Anything else? Lots of scatterers. That means you're getting multipath reflections from many different sources. Okay. They are uniformly distributed in angle. That is correct. Uniformly distributed in angle. Anything else? Non-line of sight. Okay. Outdoors. It could be non-line of sight indoors also, because there are, you could have the transmitter in the next room and the receiver in this room. So non-line of sight situations can arise, but the number of scatterers are more likely in an outdoor environment, and rarely fading would probably occur there. Okay, so but rarely fading can occur in an indoor environment also. Like let's say you're in a place where there's a lot of metal. We are doing some experiments in our machines lab. Most of you have seen machines lab. There's a lot of metal. So if there is non-line of sight inside a machines lab, then definitely you will get a lot of reflections in that environment. Okay, any other points? One thing is very, very important, no dominant path, because if there is a dominant path, it will skew the performance, it will skew the, so no dominant path is something that you should not omit. Okay, anything else? Anything else? Does it say that all multipath components must arrive at the same time? Not necessarily. You can have a time dispersive rarely fading channel. So basically, which means that you have multiple taps. Each of those taps is a combination of several multipath components, and therefore each of them are rarely fading. So basically, if you have alpha 1 and alpha 2 as the two taps of your channel, alpha 1 has got Rayleigh distribution, alpha 2 has got Rayleigh distribution. When I say alpha, it's modulus of the channel tap, which will be alpha e power j5. So alpha is the magnitude response. Okay, so again, this is something that I believe now you are comfortable with. What are the assumptions? What is the distribution that that we derived? What are the expressions for the PDF? And maybe from the CDF, the link to the probability of outage. Again, that is an important one, which gave us insight saying that you must have additional margin to protect yourself against the fluctuations that are present in the Rayleigh fading. So the notation that we will follow is that a tap or a channel coefficient that is composed of a real part and an imaginary part plus j times zi of t. Now the assumption is each of these are independent and Gaussian. They are zero mean and they have a common variance sigma squared, and based on this we say that magnitude of z of t, this we call it as alpha. Strictly speaking, you should call it as alpha of t, but again basically at a given point in time, alpha is a random variable that has got Rayleigh statistics, Rayleigh random variable. Okay. So again, this is our broad understanding of Rayleigh fading channels. Now in addition to this, we also introduced the notion of a time resolvability, and it's important for us to sort of keep that picture in mind. Basically, time resolvability in signal processing or in communications depends on the bandwidth, inversely proportional to the bandwidth of the signal, and as you increase the bandwidth of the signal, your time resolution improves. And because of this environment, it looks like more multipath can be differentiated in terms of their times of arrival. So this is more multipath components in terms of their times of arrival. So you can tell that they are distinct multipath components. Okay, so that a lot of it depends on the bandwidth of the signal, and to help us put this framework together, we looked at a channel. There is no difference in terms of the channel. The channel, if you do a wideband characterization, you will resolve all the multipath. It has got a frequency response. But if you were to transmit a GSM signal through this multipath channel at a particular center frequency, we said that it does not see much frequency variation, because it is not resolving the multipath. On the other hand, a wideband CDMA system at 5 megahertz will be able to resolve the multipath, and of course we extended it to the OFDM system as well. Now we move on to discussing the Say and Vishwanath example. Again, the notation we have kind of moved over to Say and Vishwanath's notation, so that as you read the book you will be able to follow without any difficulty. So the first three cases were already covered in the last class. I'll just refresh your memory so that we will be familiar with the notation. Transmitter, like a base station, a transmitter, that is the base station, a mobile station at a distance of r. We are looking at the electric field. Electric field is a function of the carrier frequency, the time, because it's a function of time, and the displacement vector. And u itself is a function of the displacement, the azimuth angle, and the elevation angle. So considering the movement within a plane, we can say that the received vector is some proportional gain constant gain term alpha, inversely proportional to r, which is the displacement, cosine 2 pi fc t minus r by c. Fc is carrier frequency, c is the velocity of light. Okay, that was case 1, fixed receive antenna. We move on to case 2. Now we have the mobile station moving to the right away from the transmitter at a rate of v meters per second. So the received electric field is a function of Fc and t, no change there. The u vector does no change with respect to theta and phi, psi. The only change is that it's no longer a fixed displacement, but it's an initial displacement plus v times t, where v is the velocity vector, t is the time that has elapsed. So the received vector would be alpha divided by r naught plus vt. That's your now net resultant. So basically, this is resolved into two components, r naught plus v times t, and cosine 2 pi fct. Basically, if you substitute for r in terms of r naught plus vt, we showed that you get this expression that clearly shows the introduction of Doppler shift into the system. Okay. Now, maybe it is an interesting point for us to just make a simple observation in this particular case. So if I had a signal whose spectrum was centered like this, so a baseband spectrum let us say goes from omega naught to minus omega naught, baseband spectrum, and it will be modulated to some carrier frequency, let us say it is some fc. The presence of the Doppler, what does it do to the received signal? Shifts which way? If I am moving away from the transmitter, it will shift to the left. Basically, it will reduce the carrier frequency. So it will look like that my signal has been shifted to the left, and that shift is proportional to the Doppler shift, and of course to the right. Okay. Now, one of the important things that we would like to emphasize is the order of magnitude. So, let us do a quick example that will probably help in clarifying this particular aspect. So, we are looking at a vehicle moving at 60 kilometers per hour. The carrier frequency is 900 megahertz. 900 megahertz. I want to know what is the maximum Doppler shift. Positive or negative does not matter, maximum Doppler shift. Okay. Maximum Doppler shift is FV by C, carrier frequency times velocity times the divided by the speed of light. This comes out to be 50 hertz. Okay, now here, this is the important thing is not the calculation of 50 hertz, but the relationship between 50 hertz and 900 megahertz. So you see that there is a very significant difference between the carrier frequency and the Doppler shift. So it looks like the carrier has been slightly perturbed. Okay, that is one observation. Now take the second aspect. So supposing this had been a 200 kilohertz signal. Okay, basically it is a 200 kilohertz signal. So the receive filter will have a 200 kilohertz bandwidth. Now what happens if you have the presence of Doppler? The signal looks like it is shifted slightly to the left or to the right. Okay. Now if you had your receive filter exactly at 200 kilohertz, what will happen? A portion of the signal will fall outside and you will lose part of the signal. So what is the strategy? You keep your receive filter slightly wide. What's the penalty that you will pay if you keep your receive filter a little wide? You'll allow more noise to come in, a slight penalty in terms of your signal to noise ratio and receiver sensitivity, but you will not lose the signal. You will still be able to capture the signal. Now, when we go to the third generation and fourth generation, we are talking about signals of the order of 5 megahertz or up to 20 megahertz. 50 hertz in 5 megahertz, you can't even tell the difference. So the receive filter is probably wide enough to accept this. So the frequency domain impact of the Doppler shift from an engineering intuition is not much, because the only thing that will get affected is the receive filter, and the receive filter in most cases will be sufficiently wide to capture the signal of interest. Then where is Doppler showing up? Why are we even studying Doppler if it's not a problem? In the time domain, it is far from a solved problem, because in time domain is when you will see these signal fluctuations, and that is where you will see this big fluctuations in terms of the received signal amplitude. So Doppler in the frequency domain is a impairment that you can easily characterize. In the time domain, it is not so simple. So that is what we are going to see. How is it going to affect me in the time domain? How am I going to handle this? And that's hopefully what the remaining cases of, say, Vishwanath, which should give us an insight into this particular aspect. Case 3 again is a review, so we won't spend much time. The receive antenna is fixed, that the mobile is not moving, but there is a perfectly reflecting wall. So the signal that is received at the mobile is a combination of two. One is the direct path, other one is the reflected path. The direct path is traveling a distance of r, the reflecting wall is at a distance of d. So if you take the round trip is 2d, then the distance traveled by the second path is 2d minus r. So the second term is what we need to focus on. It will be some gain alpha prime based on how much you lose in the process of reflection, and also given that the electric field is going to have a 180 degrees phase change, you will have to incorporate a minus sign also, in addition to the loss that you will occur in the process of reflection. The total distance traveled is 2d minus r, and then you substitute the expressions for the displacement is 2d minus r. Now we derived two equations from this based on the phase difference. So basically looking at the phase term of these two components, the phase difference gave us three insightful terms. One is if you interpret in terms of d minus r, that's the difference, because d minus r can also be related to 2d minus 2r. Let me just write that down. D minus r can be related to 2d minus 2r divided by 2, that can be related to 2d minus r divided by 2, and that's the difference between the path lengths. So ultimately d minus r can be related to the difference in path lengths in this particular example, but the most important thing is if your path lengths are differing by lambda by 4, that results in a phase change of pi. So this is what we refer to as coherence distance. So any perturbation which is much less than lambda by 4, you can assume will cause only a minor perturbation in terms of the phase. So if it was constructive before, it will still remain constructive. If it was destructive before, it will remain destructive. But if you have moved beyond lambda by 4, then things are likely to change. So that is why we refer to this as coherent distance. A very important quantity for us to understand by how much should you move before you start to see changes in the channel. And again, this is related to the notion that you have to change by order of a fraction of the wavelength in order to see a change in the channel characteristics. This is only a simple example, but even in a complex example, you find that this principle is preserved. So coherence distance, very, very important for us. How long does it take for you to cover the coherence distance? Depends on the velocity with which you are traveling, delta x by v, and that tells you for how long does the channel remain similar. After that, it starts to become dissimilar. So coherence time is probably a more important parameter when we talk about the receivers, design of the algorithms for receivers, because you always want to know how often should I adapt my channel estimate in order for us to be able to detect the signal. Again, we will come to talk about that more when we come to the detection methods. The same phase difference, if you were to rewrite it in the form that is given, so let me call this one of them as equation number 1, and the other one as equation number 2. The insights that we get are from these two equations. The second one says that if my carrier frequency changes by the reciprocal of 4d minus r by c, then I'm going to see a difference in terms of a change of pi. That will change the constructive addition to destructive or destructive to constructive, and we showed that 4d minus r is basically related to, again going back to the earlier expression, it is related to the time difference between the two paths. So the difference between the first multipath component and the last multipath component is what we refer to as the delay spread, and the coherence bandwidth is inversely proportional to the delay spread. Again, we also made an observation, if there is no time dispersion, tau d is 0. So which means your coherence bandwidth is infinity. So that means frequency hopping will not help. Even if you change your carrier frequency, you're going to see the same channel. But if you had even a slight dispersion, then frequency hopping is going to help, because that will change your carrier frequency, and then you can change a good channel, a bad channel into a good channel through the process of hopping. Okay, we move on. So this is now we move to case 4, where we want to derive the case. Let me just write that down. So case 4 is we have the reflecting wall at a distance d, and the RX antenna is moving at the rate of v meters per second. RX antenna moving. So more or less you would have to combine cases 2 and 3 to write down the answer that we want to have for this this particular case. Again, definitely would encourage you to make sure that you do write it down in full. So the received electric field as a function of the carrier frequency T and it is R naught plus Vt. That's your displacement now, because the mobile is moving, will consist of two terms. The first one will be alpha by R naught plus Vt, cosine 2 pi Fc. Again, you would have to substitute the expressions for R. So I will take advantage of the earlier expression. So this will be 1 minus V by C into T. That's the negative Doppler shift, because the direct component is in the same direction as the direction of motion, minus R naught by C. Okay, so that's the first term. The second term, I'm going to write it in two steps. Minus sign because of the reflection, which introduces a change, a 180 degrees phase change, and now it's again alpha dash divided by 2d minus R naught plus Vt. It was 2d minus R previously. When R, we are showing it as R naught initial displacement plus Vt. Just substitution, so nothing complicated here. 2 pi Fc T minus 2d minus R naught plus Vt. Again, just substitute systematically. This whole thing divided by C is the second term. Okay, I've just changed R to R naught plus Vt in the corresponding equation in the earlier case. If I were to rewrite this term so that we get the insights that we want. So let me rewrite it as alpha dash divided by 2d minus R naught plus Vt, cosine 2 pi Fc 1 plus V by C into T. Again, this is the positive Doppler shift, plus R naught minus 2d divided by C. Okay. So two components. The minute I start moving, in this case I have two components which are going to interact with each other. One of them has got a negative Doppler shift, other one has got a positive Doppler shift. So let's just write the following observations regarding the Doppler. So the maximum Doppler shift we are seeing in this case, one with positive maximum and the other one the negative maximum, is equal to plus or minus Fc into V by C, or this can also be written as plus or minus V divided by lambda. Okay. So that's the maximum shift that you can encounter in this. Again, we saw earlier, doesn't matter whether it's positive or negative, the frequency domain impact is not going to be very significant. However, what we are interested in is the maximum range of Doppler shifts that you will encounter in the received signal. So range of Doppler, maximum range of Doppler will be positive maximum divided by C minus the negative maximum FCV by C. So that is 2 times the Doppler shift in any direction, FCV divided by C. This is the maximum shift. So somewhere in this has to be every received component that is present. Okay. So another point that we have made is that the Doppler shift FD magnitude is much less than the carrier frequency. Again, just an observation, because in the next example we will be building upon this. Okay, is this clear? Basically what we have shown is a combination of case 2 and 3. There's a reflecting wall, you're moving to the right, there are two components. Basically there is one component with a positive Doppler shift, another component with a negative Doppler shift. That gives you a maximum Doppler range, range of Dopplers. And at the end of the day, the Doppler shift is something that is much smaller than the carrier frequency. It is also much smaller than the bandwidth of the signal. In most of the cases, we are talking about bandwidths of several hundreds of kilohertz or in the order of megahertz. Okay, now comes the last of the cases that we want to study. Again, now you may say, well, I've already exhausted all my cases, all the combinations have been looked at. No, there is actually one more very, very interesting case. Okay, case 5. Case 5 is reflecting wall, moving RX antenna, except that you are at the very close to the wall, basically almost bumping into the wall. Moving RX antenna close to wall, close to the reflecting wall. This is the scenario. So again, we don't have to rewrite, just take the equation from the previous case. In the previous case, the distances were r and 2d minus r, correct, where r was given by r naught plus Vt. Now what we are going to make the approximation is that alpha is approximately d, that is the distance from here to here, from here to here is d distance. So r is approximately d, which tells me that 2d minus r is also approximately equal to d. So which means that two components are going to be very similar in terms of their scaling, because alpha by r and alpha was, other one was alpha by 2d minus r. So the received signal vector now is going to be alpha divided by r, or let's write it as alpha by d, cosine 2 pi fc 1 minus v by c into t minus r naught divided by c. That is the first term. This is the negative Doppler shift. The second term comes out to be alpha dash. We are assuming it's a lossless reflection, so therefore the gain is also alpha here, alpha by d, cosine 2 pi fc 1 plus v by c into t plus r naught minus 2d divided by c. Now notice that this first component corresponds to fc minus fd, this component corresponds to fc plus fd. What is new? Is there any insight that can be gained from here? Turns out that trigonometry gives us a very, very good insight. Basically, we have the form cos A minus cos B. So this can be written as 2 times sine of A plus B by 2 sine of B minus A by 2. Don't worry too much about the signs. The quantity inside is the important one, but make sure that you get the signs correctly. So this expression, equation number 1, can be written as 2 alpha by d. Just 1 second, let me finish and then I will be with you. Sine of 2 pi fc into t, basically I am adding those two terms and dividing by 2, t minus dc by 2. The second term will be the difference of the two components. Notice that fc will get knocked off, but you will see that it is sine 2 pi fc v by c into t. Well, you said fc is getting knocked off, but it does not seem like, not yet. vc by t plus r naught minus d divided by c. Please make sure that you just check the algebra. The reason I said fc is sort of knocked off is for the following reason. This is nothing but fd. So I get two terms, a product of two terms. One is a sinusoid at carrier frequency, the other one is a sinusoid at the Doppler frequency. Yeah, question.
So shouldn't it be alpha by d plus vt and d minus vt in the first equation?
I'm sorry?
The scaling term?
You are at the edge, almost at the wall.
Okay.
At the wall. So approximation is that the direct path and the reflected path are traveling almost the same distance, and that's equal to the distance. There's a slight approximation involved, but if you are very, very close to the wall, this equation is valid. Okay, now the question is, what exactly did this equation tell us? Now, what are we trying to do? We're trying to get an expression for the electric field. We said that the electric field in an environment where there is multipath, one is a positive Doppler shift, other one is a negative Doppler shift, and I am moving. The reason there's a Doppler shift is because you're moving. Under this scenario, the composite signal now looks like it is a product of two sinusoids. And this, I'm sure you recognize, is nothing but what you would have encountered in what type of modulation? Amplitude modulation.
Yeah.
There's a carrier signal, there's a message signal which is at a much lower frequency. You multiply the two. So I will not use the term message. This is the Doppler component. This is the resultant signal. Resultant signal, this is for case 5. Resultant for case 5. But in general, what it shows is if you have multipath components in the presence of Doppler shifts, what is going to happen is your sinusoid is at a carrier frequency now gets modulated. So that means your electric field is no longer a constant magnitude signal. It is something where the magnitude is going up and down. And how fast is it going up and down? Doppler frequency. The faster you go, the faster this is going to oscillate. So this is the insight that we get, and it's very, very important that we are able to capture our understanding and be able to apply. So what are the things that this example or this series of examples has taught us? So if I were to summarize the Say and Vishwanath example, a very, very simple example, but it has given us the following insight. Case 2 straight away gave us the understanding of Doppler when you move away or towards the system. The case 3, this was case 2. Then case 3 gave us valuable insight in terms of coherence distance, coherence time, and coherence bandwidth, all three elements. Okay, and coherence bandwidth is inversely proportional to the time spread, or we call the delay spread. Okay, and case 4 basically combined Doppler and the multipath components, and case 5 basically gave us the effect of the modulated signal. I will put modulated within brackets because causes the signal, the envelope of the electric field to go up and down at the rate of the Doppler frequency. Okay, so this one, case 4 gave us Doppler plus multipath, and when under the right conditions, you will see that the signal almost goes down to 0 and then comes up again. So in practice, when you're adding a large number of signals, the envelope may not go all the way to 0, or it may, but still what you will see is the effect of the fluctuation, which is what is something that is we have to be careful with. Okay, any questions on what we have said so far? How does Doppler affect my signal? We have come at it from two very different aspects. The first one was we drew a lot of multipath components and then said, I'm going to characterize it statistically. Then we said, let's take a very simple example and then see what happens inside the presence of Doppler. And we have shown that there are two. Now take this understanding, anchor it in the statistical characterization. That will now tell you, okay, how easy or difficult it's going to be to work with the fading channel as a whole. Any questions? Okay, the question is, why did we call it as maximum Doppler shift? As I think I may have mentioned earlier, the maximum Doppler shifts happen when you are moving in the direction of propagation or away from it. Right? So anything, if you're moving at an angle, will be less than that. So this is like the worst case that you will encounter. One side is maximum positive Doppler, the other side is giving you maximum negative Doppler. Okay, so that it's a specific case to highlight the fact that this is the worst case shift that can occur in the system. Okay. Good. We move on to the other elements that we want to cover in today's class. Now, another aspect that maybe I wanted to highlight to you is the notion of the change from AWGN to fading. And as we mentioned in the last class, the goal of wireless communications is to see if we can move the fading BER performance to the AWGN performance. So from a statistical description, I am trying to change the channel statistics. Channel statistics, when I have non-line of sight, large number of multipath components and no dominant component, this is going to give me Rayleigh. Now, the whole goal of our study together is to change the standard statistics. Basically, when I draw the pink line and say that is n equal to 2 antennas, you may say yes, in a sense, because I can always choose the better of the 2 antennas, or I can combine the 2 antennas and make the detection. But at the underlying it, what have you done? What you have done in the case of you have changed this channel statistic. It is no longer Rayleigh. Okay, so our goal is to find ways in which we can shift the performance away from Rayleigh, and the ways in which we would do that, possibly through FEC, possibly through antenna diversity, maybe through frequency hopping, or combinations of these things. All of these are attempts to change the statistics, to make the channel look slightly different from what it naturally occurs in the wireless channel, and to make it more favorable for us in terms of the transmission of the data that we are interested in sending across. Okay, what we would now like to move forward is to understand the BER and the link to the modulation scheme. Ultimately, you know that through the system design, you have a certain signal to noise ratio, or a signal to impairment plus interference plus noise ratio. So from your system design, you know the range of SINR that you will be able to offer to your receiver. Now, SINR will tell you what the BER is going to be. SINR tells you what the BER is going to be, and depending upon the modulation, you will have different BER graphs. So then once you know the SINR, once you know what is the target BER, so SINR is from system design. That is from how you have designed the transmit power, how much antenna gain you have done. The BER is your user requirement. User says I must have 1% BER or better. So there is a user requirement basically, or applications requirement. So there are two different entities that come in, and then you say, okay, this is the SINR I have from the system design, this is the BER I must achieve. So therefore, what is the modulation scheme that will satisfy the modulation index that I am interested in? So the criteria for choosing a modulation. Again, we will approach it in a very intuitive way in this lecture, and then build the detailed in the next one. So the first one is you must have acceptable BER in the range of SINR that you have. Acceptable BER is the first and foremost requirement. If you have poorer SINR, you will go for modulation schemes like binary or quaternary. If you have very good SINR conditions, then you may go for 16 level modulation or 64 level modulation. So the other element that also important is what is the how robust is the modulation? Robustness to multipath. Robustness to multipath, and multipath we are more specifically concerned about ISI. If there is no time dispersion, it will be Rayleigh fading. So you will bring that case also. But if there is time dispersion, there will be intersymbol interference, which means that then you will have to have an equalizer. So this will automatically require you to have an equalizer. So you want to choose a modulation method that will have an equalizer complexity that is manageable for your receiver. Then in the case there is no time dispersion, you will still have fading. So again, in the presence of fading, you should have good performance. So you should have the ability to introduce diversity, different types of forward error correction, the corresponding decoding methods, frequency hopping maybe, whatever are the techniques, and your modulation method must lend itself other changes that you can. And in a cellular type environment, we always have to worry about it being an interference limited environment. So therefore, we also talk about what are some interference suppression methods. Interference cancellation may be one, interference mitigation, there are several ways of which. So interference mitigation, how easy or flexible that it will be to do the different interference mitigation methods. And there is a third element that we are always very interested in, it is called spectral efficiency. Spectral efficiency, and it is measured in bits per second per hertz per dot dot dot. What are the dot dots? It could be per cell, you may be measuring your spectral efficiency per cell, or you may be measuring it per user, how many bits per second per user are you able to get. So there are several measures depending upon what particular aspect that you are looking at, but at the end of the day it is bits per second per hertz. So bits per second corresponds to the speed of transmission. Speed of transmission, how many kilobits or megabits per second are you transmitting? Then this is the bandwidth that you are using. So are you efficiently using your bandwidth? For a given bandwidth, what is the maximum data rate that you can achieve? That is bits per second per hertz. But then there is frequency reuse, there is all the system design aspects. So how do I actually measure it? I should measure saying I have so much spectrum across my entire cell, but within one cluster these are the number of users I can support. So it is per user or per cell, sometimes per sector also, again depends on how you want to look at it, but the bits per second per hertz very, very important, you want to do that. Now very often books will stop with this 3. You must get good bit rate performance, you must have a system that is robust to the different types of impairment. What are the different types of impairment? Fading, multipath, which will result in intersymbol interference, and co-channel interference. Again, 2 types of interference that we are, equalizer will mitigate the intersymbol interference, and you must have other techniques to mitigate the co-channel interference. Spectral efficiency is very important. Now there is yet another element that is that one more aspect that needs to be added. So but let me ask you this from in a slightly different way. So at a given EB by N naught or C over I, okay, that means either in noise limited or interference limited, the following statement is true. There are 2 binary modulation methods. One is GMSK, we said that this is the modulation method used by GSM and others, and then there is of course BPSK. Both these are binary modulation methods. Binary modulation methods. So here is the following statements are correct. For a given EB by N naught or C over I, the bit error rate of GMSK is higher than the bit error rate of BPSK. So which is the better modulation? BPSK is the better modulation. Okay. Now it turns out that the complexity, the receiver complexity of GMSK is actually also higher than receiver complexity of BPSK. Actually receiver complexity of BPSK is very, very straightforward. So this is also the case. So the question is, why did they choose GMSK for GSM? They must have known that these 2 are obvious results, everybody knows about it. The third or the fourth component that we should not overlook is the power amplifier efficiency. Power amplifier efficiency, it says that how much efficiency can you get out of your power amplifier. The higher the power amplifier efficiency, the better, because that means you will draw less power from your battery and your device is going to last longer. So power amplifier efficiency, we call it as PA efficiency. It depends on the linearity requirement. How linear should you want the power amplifier to be? and the linearity requirement for BPSK is much higher than GMSK. So GMSK actually runs at higher power amplifier efficiency. So at the end of the day, if you wanted to build a device that is battery and power efficient, then GMSK wins over BPSK. But all combination of all four need to be taken into account, that we get a good understanding of the modulation methods. Okay, so 2G, we used GMSK. Then comes 3G. 3G are the following methods that we have used, or modulation schemes that we have used. GMSK continued to exist, so basically these are the methods, these are the things that we have added. QPSK, we added 8PSK, found that it was very difficult to work with 8PSK, and also introduced 16QAM. Okay. Then came along 4G. We saw that we could now do more processing at the receiver. We also know that some of the users are going to be in good channel conditions. So the modulation methods are QPSK, dropped 8PSK because of complexity reasons and performance reasons, 16QAM and 64QAM. Okay, and 5G, all of this plus possibly 256 QAM. Okay, so we are seeing the fact that we are able to get the maximum out of the channel, but again the complexity of the receivers is growing very fast, and we have to be aware of that. So basically at this stage we were doing 1 bit per symbol, 1 bit per symbol or per channel use, went all the way to 4 bits per symbol, then came to 6 bits per symbol, the highest. So this will basically improve your spectral efficiency, and this is going to 8 bits per symbol. So in a sense you are achieving something like 8x improvement over 2G when you move on to this side. But again, it's not strictly 8, and there are several other factors that we need to take into account. It turns out that it's a factor that's much larger than 8, but simply from a spectral efficiency point of view, 1 bit per symbol was what you were transmitting through the channel. Now you are transmitting 8 bits per symbol. Again, a very significant difference and a significant change. Now let me move on to highlighting one more important element. The received signal in AWGN. R of t is the transmitted signal plus the noise, AW, that is the additive channel noise. So detection is straightforward, you have already done it in your computer simulation example. Now I am going to write down 2 cases, the case of a fading channel. R of t is equal to alpha of t e power j phi of t, that is my complex gain term which represents the fading. This multiplied by s of t plus eta of t. Okay. Now the reason I said I have to take 2 special cases, this is flat fading. There is only one channel, one multipath channel that is present. Now the other type of fading channels will be frequency selective. That means there is time dispersion. Frequency selective fading, that means there is at least one additional multipath component. So it will be R of t is equal to alpha 1 t e power j phi 1 of t s of t plus alpha 2 of t e power j phi 2 of t s of t minus tau 2, so some delayed version, plus more terms like this depending upon the number of multipath components, plus the additive Gaussian noise. So basically the noise is still present, there is interference happening between the different multipath components, and that is frequency selective fading channel. Now an important point to note is that in all of the modulation methods that we talk about in 2G, 3G, 4G, the information is contained in amplitude and information regarding the user information. User information is present both in amplitude and phase. is encoded in amplitude and phase. So, which basically tells us that in order to do the demodulation process, one of the first things that you must do is to actually estimate the fading coefficient. So, without that there is no way we can detect the signal, because this phi, if you assumed it was 0, you will make an error in the transmitted signal, because you could be in the wrong quadrant. Alpha of t, if you assume that is equal to 1, you may not be able to differentiate between the different QAM symbols. So again, this is very crucial. So any time you want to do what is called coherent detection, so coherent detection requires us to estimate coherent detection, means that I must estimate all the alphas, alpha of t e power j phi of t, and maybe I will just put a coefficient k, so that we recognize that there will be several of these. So k equal to 1, 2, 3, however many, you must estimate them, and you must estimate them correctly. And this is the reason why whenever there is transmission in a wireless system, what happens is, if you notice in GSM, right in the middle there was some what we called as overhead information. This is the overhead, and this is the user data that is present, user data. So what is the overhead for? To estimate your alphas, estimate the alphas and phis. Okay. So very important. And why do you keep transmitting? The next time you want to do a transmission, again you transmit overhead. Why? Because the channel has changed. Now how often do you must transmit this information? Coherence time, because you want to make sure that when the channel has changed, you must be able to re-estimate the channel. So this distance between the times that you transmit the information must be less than coherence time. This should be less than coherence time. Okay. So that is the strategy that we want to have. Now even if you have designed using coherence time, there is one very fundamental problem that you will encounter. Can you tell me what that problem is? I have designed my system very correctly. I have designed them to have the overhead at the correct repetition rate, so that I will get my estimates, so that I can do coherent detection. What is the problem that I can run into? Okay, I hear the correct answer. The correct answer is fading. What happens? The channel, let us say, changed. Basically it went through a fade. The coherent detection basically will lose track of the signal at this point. When you have gone into a fade, your coherent detection will lose track of the alphas. Okay. Now after the fade, the signal may come up above the level that you can detect, but you cannot detect because you have lost track of the alpha. So this is a serious problem, because what happens in a typical coherent detection, this is the bit errors. This is the 0 level, 0 0 0 0. At this point you hit a fade, error increasing, every symbol is in error. Basically beyond that point where a fade occurs, you will have a large number of errors happening. The only way you can avoid this happening is you transmit your overhead more frequently. What happens if you transmit overhead more frequently? You will lose user data rate. So overhead is really wasteful information from a user data point of view. So that constant trade-off says, how often should I transmit my reference or overhead information so that I can get robust detection? Now the question is, can I get away without transmitting any reference information at all, overhead information? And it turns out the answer is yes. So no overhead. Okay, because I don't want this overhead, because I don't know how much overhead to put. So is it possible? The answer is yes, for flat fading channels only. and that is a method called differential modulation, which we will explore in the next class. So, differential modulation, I am sure you would have studied it, but please do look it up. Any of the communications textbooks would give you a good reference, differential BPSK, differential QPSK. So, it is possible only for non-frequency selective, otherwise, in other words, it is flat fading is the condition. You will find that it is a very robust modulation that is used. And how does differential modulation work when coherent does not work? We will see in the next class. Thank you.